Good. Anybody do anything interesting or fun or interestingly fun or fun? Ooh, which barbecue? Which barbecue?
Ribs,
Nice.
steak,
Cool.
burgers.
Welcome to fall, right? I guess it's now that it's after Labor Day, we have to stop wearing white. It's after Labor Day. So we can get our pumpkin spice toilet paper and our fall things. We can start tucking our buttoned in shirts in and all that kind of stuff. What a lovely time of year it is. And the weather accommodated. Fall is now in full fall here, and so it's going to rain for 3 days. Yay! You know how it does. This is traditionally one of the worst traffic days of the year. It's like, because traffic's always worst on Tuesday. Traffic is always worse on Fairfax County on Tuesday. And it's like a rainy Tuesday morning is like, ugh. It's like the nightmare scenario. But you all made it, so that's great. How'd the homework go? I know, really, we've been doing this for weeks, you know, and so it's like, this is literally the only thing we do. I come in here, I futz with technology for 10 minutes, and then we draw molecules. So it's like, if you don't have it by now, we have plenty of other wonderful Fairfax County high schools we can send you back to. I mean, really, and you have another homework assignment due, what is that? Is that Thursday? Get to drawing. So a couple of questions might have emerged recently, like the one that I get more often with than not, with the draw the different macromolecules one, is how much detail are you looking for? How much detail are you looking for? With the carbohydrate, pick one. Pick one, right? Unless it's specific, in which case draw the specific one. Carbohydrate, every atom. Every atom. The amino acid, every atom. The triglyceride, most of the atoms, but you don't have to do all for reasons which we'll talk about in a bit. And the nucleotide, every atom. Every atom, okay? So it's like, I'm gonna draw, what is it, like RNA or whatever it might be, and it's like, ooh, it's swirly. It's like, yeah, we're not there. Okay, so this is not like, what does it look like in a drawing that you would see in 3rd grade? It's like, give me some detail on this thing. Welcome to college. Show me the deets. You know the rules of how many bonds things can form at this part, right? If you see some hydrogen, you better only have one covalent bond coming out of that thing. If there's oxygen, you better have 2, or if you have 1, you better put a charge on that thing saying that it's a free bond you can make that has a charge associated with it. Sometimes we can get. If it's nitrogen, you better have, if you have nitrogen, you better have 3 bonds on that thing or charge it, one or the other. If it's carbon, you better have 4 bonds on that thing, or it's just wrong, right? I've never seen charged carbon out there. It's just F for you, and F for you. How do you go from carbon to fluorine, right? You don't put 4 bonds, you go from a C to an F, right? I'm not getting it right. I just made that up. I'll work on my delivery. That might be why it wasn't so good. I'm going to show you carbohydrates, and then we're going to talk about how to link molecules up, and then we're going to talk about lipids, proteins, and nucleotides, okay? So the question might be, why not talk about how to link molecules up first? And I would say, well, it's because we need something to link. So we'll make something that we can work with, then we'll talk about some linkage chemistry, then we'll talk about some more detailed stuff. What is a carbohydrate? What is a carbohydrate?
Anything that has CH2 in it.
Sorry. Like to the X power, right? I shouldn't say power, to the X multiple. So glucose, fruit, they also end in ose. So if you see a molecule in the back of a cereal box or something, and it has a chemical that ends with ose, O-S-E, carbohydrate. Fructose, glucose, galactose, lactose, maltose, ribose, ribulose, galactose, right? All these oses. Oses are the carbohydrates. Perfect. They exist in two different arrangements when we see them. I'm going to draw a typical 6-carbon sugar. And typically when I draw a sugar, it's a 6-carbon one, usually because we talk about glucose so much as the body's currency. It's a good one to just sort of repeat sort of over and over. And it's a good 6-carbon C6. So kind of like that. We would say this is like the sort of the linear version of it. Anybody see anything wrong with this? The diligent student who studies, who looks for a career that will pay off, should be scratching their head right now saying, I think you screwed something up. What's going on here? Yes, there are too many. It doesn't follow the CH2O rule. The linear forms typically don't. When we draw these linear forms like this, a lot of times we draw them in a neutral state so that all of the spaces are occupied. To actually be the CH2N, it would have to be like, it'd have to take 2 of these hydrogens off, which we really don't do in the linear form by convenience. But these hydrogens can sort of come off when they do. So a lot of times when we draw the linear forms, they will have like two additional hydrogens attached to them. That doesn't change the original definition. When we actually draw the other version of them, that they will spontaneously sort of form into, we say this is the ring or the circular structure. I'm going to draw it like this. Draw our OHs. Nothing there, right? That good? Because of the way we have this organized, we lose 2 hydrogens in the structure of it. So now it has the appropriate number. So the ring structures are what we refer to when we look at the CH2O version of it. Go ahead.
So why would you connect like the 5 C's connecting to the O instead of
Yeah, what's up with that oxygen, right? So it's like you think if it does a ring and it rings together, it would be a 6-carbon ring, which is what you oftentimes see in organic chemistry, and all the other stuff, the oxygen, the hydrogen, and the nitrogen, be off to the side. The sugars don't do that. With the true carbohydrates, one of the linkers is always the oxygen. Yeah, weird. So the carbon chain is not like 1, 2, 3, 4, 5, 6. It's 1, 2, 3, 4, 5, and the other one almost like forms what you would say this is a methyl group with a hydroxy stuck on the end of it. Hydroxy methyl glucose. it'd be 6 or 5 hydroxymethyl, something weird like that. So what's fun is that when you read textbooks, it says that the sugar molecules sort of spontaneously bounce back and forth between these two configurations, which is true. They will. They will. It sort of depends on what you're doing. When you're carrying sugars around with you in your liver, we'll talk about this in just a second. When you're carrying sugars around in your body for storage, like as glycogen in your liver and things like that, you lock it into an arrangement like this and you store it thusly. However, when you're going to take sugars and run them through respiration and start getting the energy out of them, you will convert them in the linearized form and you will start breaking it between the 3rd and 4th carbon. So it sort of depends on what you're doing. If you're going to use them for energy, like short-term energy, you eat some carbohydrates and you're going to run it through respiration, mitochondrial processes. You'll convert it to the linear form. If you're going to store them longer term, you'll go with the circular arrangement and lock them into place in the liver that way. But you would call them both the same thing, right? They still have the same name, but it arranges itself as 2 different arrangements. That makes sense? Let me go back. I'm not going to ask if it makes sense. Is that clear? It doesn't have to make sense yet. Sense comes later. Sense comes when you sleep and when you go for a run, right? It'll come to you tonight. But can you live with this as something that is 6 in truth?
So are you saying that the linear is wrong?
What?
Are you saying that the linear one, the drawing is wrong because it's too many?
No, it's right. But when we have that CH2O definition of a carbohydrate, it refers to the circular form. When it linearizes, it either ionizes or it adds hydrogen to it if it wants to be neutral. But which is easy to do. There's plenty of hydrogens around. They're free floating in solution, a la pH. Correct? I mean, hydrogen or ions are cheap and abundant out there. They attach all kinds of stuff. Cool. So when I draw little sugar molecules, pretty much from here on out, I'm going to do it like the laziest way possible. It's just going to be like that. I'm not even going to draw the oxygen. I'm not going to say where anything is. I'm just going to draw little hexagons thusly. This equals this. Okay? Good? Perfect. Let me take a picture.
How'd you get H equals 12?
On which one?
The ring form?
Is it not 12 yet?
Like, are you counting the H's also in the hydroxide?
Yeah.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Yeah.
12. I missed one.
Oh,
Yeah, 12. Yeah. All the H's. All the H's.
Isn't that line connected to the C though?
Yeah,
It's not.
Like the C to the C?
Oh, yeah. That. Oh, where's my other one then?
it's over there at the bottom, right?
Ah. Let me count my hydrogens.
Because like you connected 2 of the C's with 1 H, right?
Yeah.
Shouldn't it have its own for each? Oh, wait for the next.
1, 2, 3,
Wouldn't it be on the bottom of
4,
the right, the most right seat?
5, 6, 7, 8, 9.
See, what, I'm confused, like why you connected 2 C's with 1 H?
Connected.
And not did that with the rest.
I'm convinced this is due to my like horrible handwriting. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where's my other? I'm missing one.
It's the C on the right.
This one?
Yeah, because you connected.
I'm counting this one twice. That's my problem. Okay.
So each should have their own.
I was like, what? It's like I'm missing. I was counting this one from that one and that one. I was like, what am I actually doing? Okay. Got it. This is a testament to a good handwriting. Okay, that's 12. That's 12. My apologies for, this is what happens when I think faster than I can write. My apologies.
You're good.
Not as clear as it could.
And the C, you know the C that's connect, like the extension, the extended C? The,
This one?
yeah, so the
Okay.
reason why the one below it doesn't have an H is because it's counting the one from the top?
1, 2, 3, 4. It's already got 4 bonds.
Oh, okay.
Yeah, it's already got 4
Okay,
bonds. So it's like it's out of valence electrons to share.
right, okay.
So it's like we desperately want it to have a hydrogen, but it can't. Its hands are full.
Just kind of homework where we're supposed to draw who's closer to draw either one of those.
Yeah, either one. It's fine. If I'm not clear or specific, then either one is. Or if I'm not specific, either one is fine. Because they both are like glucose. And to be perfectly honest, it's like I don't actually know what I drew. This might be lactose. This might be galactose. This would be, it's like I drew something. I wasn't thinking about where the O's and the H's go. But either the linear or the circular you can draw. This good? Perfect. All right. Raise your hand if you have a liver. If you're not raising your hand right now, you should be raising your hand right now. You all have a liver. Raise your hand if you have eaten liver of any beast, anything. Not like it doesn't just have to be human. It could be anybody's liver. Hannibal Lecter over here. Some fava beans and a nice Chianti, right? Chicken livers are good. Make good pate. Right, all kinds of good stuff. Tasty. I don't do it often though. Oftentimes when lions and tigers eat small-hooved animals, the liver is the first thing they go to, if not the second. They either go for the liver or the small intestines because they go for the things with the highest caloric density first. And that's either going to be like small intestines or liver, which makes sense. So if you're ever, never mind. What do you do with it? You do all kinds of stuff with your liver. One of the things you primarily do with it, detoxify stuff, detoxify things, which is good. And another thing you do with it, store glycogen. Mullet going on, little awesome mustache going on. Goatee or no?
Yes.
Sure.
If goatee or soul patch?
So it looks like the drawings I have about tomorrow.
Food goes there, right? So you take food and you put it into which hole? That's why it's oftentimes referred to as a pie hole or something like that. You put food in your face because that's the front of the tube. When we get into biology 102, we'll learn that with animals, what defines them almost more than anything else structurally is that they are tubes, and every part of them is arranged around that tube. So you put things in one side of the tube, in a day or so later, we'll see them again as they come out the other side of the tube. Correct?
Yes.
Everybody poops, right?
Yes.
So you're a tube. You're a tube. And so everything in your life is about negotiating yourself around that tube and what goes in what end and at what time. Good, clear, perfect. So food goes there. Eat it, yay. You have this thing called a stomach. You've heard it?
Yes. Yeah, we all have it.
You all have it. Poop comes out here. This is not like to scale or accurate. This is just like a purely schematic diagram that represents things that you probably already know about your own anatomy, correct? Good. Perfect. You have a small intestine where a lot of digestion can happen with lipids and proteins, and where a lot of absorption happens. That's where nutrient absorption actually occurs. So when you eat something, you swallow it, and your stomach digests it, which is just the process of taking things that are big and breaking them down into the sizes of things that are small, right? You take big things and you make them small by chewing, then you swallow it and you take the small things and make them even smaller by digesting them in the stomach. And then you plunger them into the small intestine where they're finally small enough that they can start to be absorbed into the body. And absorption happening all the way down here is a real phenomenon. Even when things are in your stomach, when things are in your small intestine, they are still technically outside of your body. And this is actually more important than you would think. The inside of your intestines is the outside of your body. To get into your small intestines, you don't have to cross any membranes, any barriers, anything, right? You could take like a small metal washer on a string, a long string, and swallow the end of it and wait a couple of days. And you can still have the one end of the string on this side and the other end of the string coming out the other side of your tube on the other side. At no point did it actually enter your body. No membranes were crossed, right? You with me on that? So it's like your body is like what happens between the outer membrane of the small intestine and the inner membrane of the skin. But you're a tube. You have this hollow environmental space that runs kind of down the middle of you. That makes sense? Perfect. So in the small intestine is usually where things start actually moving across the membrane and going into your body. And so you have a lot of circulatory system, capillaries, arteries, and all that kind of stuff feeding your intestines to distribute that stuff. The first stop for all of the blood as it takes up nutrients and everything out of the small intestine is the liver. These all gather together into a structure called the hepatic portal vein. Who's taking anatomy? Anyone? You know about the hepatic portal vein, right? Yeah, it connects all the intestinal tract to the liver. Right. Very good, very good. So all the toxins, all the sugars, all the stuff that you want, all the stuff that you don't want, goes immediately to the liver for a fast check. Before you're born, your umbilicus, your umbilical artery, goes into the liver as well, which is kind of neat. So even when you're getting nutrition from mom eats stuff, goes into the placenta, goes into baby, goes straight to the liver, just in case mom ate something that wasn't so hot either. So liver's pretty important that way. Get rid of the toxins. We'll talk about that more when we talk about cells anatomy and organelles, and does things like sugar balance. If your blood sugar is already fairly high, all right, and you don't want to put even more sugar in your blood because your sugar balance is already kind of all right, it's usually around 100, milligrams per milliliter, something like that. I don't know what average blood sugar is. It's something like that. It's like around 100. This is typical blood sugar. If your blood sugar is already high, your liver will say, okay, you know what? Blood sugar is already high. We don't need to add any more. Let's hold on to this sugar that's coming into the body, and we can store it for later. You got that? And so Mr. Pancreas over here will say, got it, and it will produce insulin. That insulin will then get detected by the liver, and the glucose molecules with insulin present will make stuff called glycogen. So what glycogen is, so you have glucose, like that, yes? Bunch of glucose molecules, correct? And it will convert them this long chain, like this, a little more dense, out of solution, right? Stored in the liver for intermediate term storage, glycogen. So it's what we say, we call this a polymer of glucose. Each individual one then being monomers. So when blood sugar is already up there kind of fine, blood sugar is nice and level, healthy limits where it's supposed to be, and more sugar comes in, insulin will be released to take the excess, detect that insulin being then picked up by the liver, converting glucose into glycogen, which is going to stay in the liver. So more sugar, because insulin is working like it should in the liver, is not going to be contributing to higher blood sugar levels. It's not going to go up into the 200s, 300s, 400s, which might not be as hot for you. Every diabetic in the room right now is saying, right? Right? We don't need our blood sugar in the 400s. Very good. Sound good? Is that clear? Released by pancreas. Sound good? Questions about this so far? Of course, we can make this reaction run in the other direction. If your blood sugar starts to get low, for a variety of reasons, either you're eating a lot of fats and proteins, you're doing either a paleo or a slow carb thing or something like that, and your blood sugar starts to get kind of low, or it's been a while since you've had a carbohydrate, or you just did a whole lot of exercise and you're burning through a lot of carbohydrates on board, you will send this reaction back in the other way. Your body will say, ooh, okay, cool. So blood sugar is getting low. Let's back convert some of this glycogen back into glucose and let it back out into the body. A different enzyme called glucagon will come in and do the opposite. So when blood sugar starts to get high, insulin released to store it as glycogen. When blood sugar starts to get low, glucagon released to turn the glycogen back into glucose to get your blood sugar back up. So right now, with that beverage on your desk, you are probably releasing truly astounding amounts of insulin. Truly astounding amounts of insulin going into your body, grabbing excess carbohydrates, storing it as glycogen in your liver for later when you can release it back into the body as glucose when you're eating it. Right? Or you go to Pasta House, and you get the never-ending pasta bowl and the breadsticks, which used to be a lot better than they are now. Anytime, and it's fine. You can eat a lot of carbohydrates and be totally okay. I mean, carbs sort of have a bit of a bad rap. As long as your pancreas and your liver are working fine, and you don't have any outstanding congenital things going on with insulin detection or anything like that, this works pretty effectively. Blood sugar can go up a little bit until the system takes over and brings it back down, and everything is good.
I think that unit it should be mg-dl.
It might be, yeah. It's that seemed like a lot of. I think you might be right. I was like, milliliter sounds like a lot of sugar. That's pancake syrup. I think I had my unit wrong. That sounds correct. Liter is too much. It's it's either a centiliter or a deciliter. I think you're right. I'll take that one. We can confirm this, but I think you're right. Cool. So then the practical everyday question would be, if you are, or if you know someone, or if you've heard of someone that has a diabetic condition, without getting into too much detail of type 1, type 2, type 3, and all this kind of stuff, something is working right here. Either your pancreas is not producing it, or your liver in your body and your cells are not detecting it, or something in between. You can do this reaction if you're diabetic just fine. You can take glycogen and you can use glucagon to convert it back into glucose. However, if you're kind of latent diabetic, hanging out with a diabetic condition, you don't have a lot of glycogen in your liver to start with, right? So it's like going this way is fine. Going this way has challenges. So if your blood sugar starts to get low, it's like, ooh, I need more glucagon. No, you don't, right? There's not much here to work with. So moving in this direction is sort of the ongoing concern of the diabetic. So you keep a couple of grapes or a jelly bean around, kind of whatever. Or if you're just not producing diabetic, but if you're not producing insulin, but the rest of the system is fine, you can do insulin injection, and you can temporarily bring this up and level you out, without getting a spike as well. So that's that system. But I said I was going to talk about making connections. So what is the nature of this arrow right here? How do you go from monomers to polymers? Do you understand the concept of a polymer? A locomotive train with a bunch of cars is a polymer of individual train car monomers. Who likes Legos? Polymers, right? You have a bunch of Lego blocks and you can build them together into larger structures that are polymers of Lego. What else is a polymer out there? Like a brick wall is a polymer of individual bricks. We could go too far with this. You get to learn about your liver today. That's actual Bio 102 content that you have today. You get your money's worth. If I have two carbohydrate molecules like this, I can join them together. You know what Santa Claus's favorite functional group is? Hydroxide. Ho, ho, ho. So every December we start to see a lot of hydroxy Santa out there. Hydrobiological humor is lost in this class. How do we combine these things together, right? I mean, that's sort of the question. And earlier I was saying the advantage of functional groups is that one of the properties they have is they make it easier for things to sort of glue together. You can bond things together with functional groups. And this is the first example. Can you make anything interesting or compelling out of these two functional groups? If you shuffle these molecules around, what could you get? Ooh. Or, we don't have to use all of them, we could just make some. What's abundant in common out there on this earth? Water, yay. We can take one of these two of these H's and one of this O's, this OH and this H, make a molecule of H2O. And in doing that, and we're not breaking bonds and making bonds. We're shuffling electrons amongst shells, and we're making what were two monosaccharides, and we are making a disaccharide. What do you think? Make sense?
So you just leave the what's left, the O.
Yeah. Yeah.
It'd be the same if you kept like the two H's too. It's still the one disaccharide. Like the two H's below it.
Yeah, these are just like,
Then it's still there.
they're just sort of along for the ride. Yeah, they're along for the ride. This right here, that bond, called a glycosidic linkage. And this reaction is called dehydration. Why do we call it dehydration? Why do we call it dehydration? Why do we call it dehydration?
The water's leaving?
Yeah.
Because what?
The water's leaves.
Yeah, the water comes out. Water comes out. It dehydrates the bond. It dehydrates the bond.
When you eat sweets.
When you eat sweets, you're usually eating a bunch of, yeah, you probably dehydrate a lot.
If you just eat. Okay. Because the sweets.
Well, it depends. It depends. Yeah. So if you're eating a lot of like molecular sugar, like just like a glucose tablet or a hunk of candy or some extreme sour heads or some warheads or some sour gummy tape or some sour gummy worms,
You don't keep making this linkage.
right? You're eating a lot of this stuff, and it's going to turn that into,
Polymer.
it's going to turn this into, diabetes notwithstanding,
Oh.
right? Some glycogen. And in that, you're going to be actually producing a lot of water as a side effect of that. We actually refer to this water that comes out. Call it metabolic water. It's water that you make. About 10% of the water that you use during the course of a day is actually metabolic water that you get from making polymers, which is kind of cool.
Where does that water go? Just in your body?
Yeah, in your body, right, into the cellular matrix, interstitial fluid, all that kind of good stuff, right? This all make sense? Am I doing okay?
Yeah.
Questions?
Are you saying that one disaccharide and a water plus water is dehydrated?
To go from two monosaccharides to one disaccharide it's a dehydration reaction. It's called a dehydration reaction because you have to pull that OH and that H out. You make a molecule of water when you bond these two together into a glycosidic linkage. You've gone from two monomers to a polymer. You've gone from two monosaccharides to a disaccharide. You've gone from two molecules to two molecules, but now the big one is bigger and you poop water out. Well, you don't
So
poop
that's
it.
dehydration.
You would pee it if anything, yeah. But you don't, you just use it for something else somewhere in the body.
Oh.
Go ahead,
Why can't you just make another H2O with what's left?
why would you? What's your objective here? Is it to live on Earth or is it to make as much water as possible?
No, that's not possible.
I mean, why does this reaction happen and not the, why don't you just take the rest of this and make another one?
Right.
You don't have an enzyme for it, is the bio answer to that, right? You can only do what you have enzymes to do, right? And you have an enzyme that will take these two monosaccharides, dehydrate them into a disaccharide, right? You don't have an enzyme that takes the leftovers and makes another one.
Oh.
If you did, you would have like well, you'd have to attach something else to the carbons because you're short on covalent bonds.
Okay.
And then you'd
okay.
have to like,
Yeah, yeah,
and then it's like, then you'd have a carbon-carbon bond. Good luck breaking that, you know, so, cool. So let's say that you had a lot of pasta yesterday and you decided to change your your sugary ways, and now you're gonna go on the paleo diet or keto or something like that. You're gonna have no sugars at all. You have all this glycogen in your liver, and you're going to crash a little bit. It's not going to be fun, or pleasant, or comfortable, but your body will adapt and will adjust. And you need to start breaking these molecules apart back into the monosaccharides so you can use them in cellular metabolism. Is there anything you can do in order to break them apart? If you use dehydration to make this reaction go this way, how would you split those molecules apart? To put them together, you took water out. To split them, you put water back in. You drive the reaction this way. And when you drive it the other way, you call it hydrolysis. From the roots, hydro, meaning water, lysis,
A lot.
splitting,
Oh.
splitting. So anytime you see a science word that has lysis on the end of it, you're talking about breaking or splitting something. So hydrolysis. What else? Anything with lysis on the end of it. Very cool. Questions, comments, thoughts?
Me?
Yeah, you?
No.
So make sense?
Yeah.
Perfect. Questions, comments, thoughts? Questions, comments, thoughts? Questions?
What's that word under hyperkick? Hyperkick.
I'll just rewrite it so it's clear. Hepatic portal.
Portal.
It's a hepatic portal vein. And it's short. It's only, who's dissected a human body before? It's only about this long, right? It takes all the mesenteric veins when they all come together to form the hepatic portal vein, which takes all that blood from the intestines over to the liver, where this decision gets made. Questions, comments, thoughts? Go for it.
Hydrolysis happens when you're trying to go from glycogen to glucose. Is that what you're saying?
Correct.
When your sugar.
Correct. Correct. You dehydrate it to make the glycogen, which will drop sugar, blood sugar. If you need to bring blood sugar back up, it'll hydrolyze, making the monomers again.
Okay, so,
You don't have to raise your hand again. You still have the questions.
okay, so I remember like this, okay, weird story. I remember one time I was playing a sport and I guess like,
You're playing a
something-
sport?
yeah, I was playing basketball and like.
That is a
something-
sport.
Right, and something happened where like the nurser was like, her sugar dropped and they gave me like candy. So is that because like,
Somebody else's sugar dropped and they give you the candy?
no,
Your sugar
like,
dropped
the
and they-
nurse told me that like,
Oh, okay.
I didn't understand what she was saying, but she just gave me a candy and like I felt better. But is that because like my body just doesn't have sugar enough? Like you need candy.
Yeah. Distance runners, anybody? Anybody distance runners? If you're doing distance running, they call it the wall. You hit the wall. Usually happens around the 20-mile mark if you're really going hard. Or if you're newer to running, it happens around the 8 or 10-mile mark. You have about 2,000 calories of sugar content that you can use during the course of a day. The thing about carbohydrates, your body can metabolize them very, very quickly into ATP to use. Great, right? You wake up in the morning, you get about 2,000 calories worth in your blood or in your liver, in your muscles and things like that. After you burn through those 2,000 calories, you start doing a metabolic state that does more fat metabolism and protein metabolism, mostly fat metabolism. It doesn't happen as long. You're going to get some cramping. You're going to get some dehydration. You're going to, you're going to kind of feel sluggish and kind of shut down a little bit.
So
Right. So what people do if they're going to do like really extended aerobic exercise tomorrow, they'll engage in a behavior referred to as carbo loading. You've heard of carbo loading. If you're going to run a marathon tomorrow, you'll eat a lot of pasta today. You can temporarily give yourself a really high glycogen glucose content
So
overnight.
when you're doing a lot of exercise, you're breaking glucose.
Yes.
Basically? So
Yeah.
you're doing hydrolysis.
When you're doing if you're going to hit the elliptical for a half an hour, right, in your yoga pants and your whatever, and you're going to listen to like the flash dance thing and watch some TV while you're doing it, you're really not breaking anything substantive. You have enough sugar stacked in your muscles that it's like you can go for half an hour and you'll be fine, right? You're not doing any large scale liver-based metabolism by burning a couple hundred calories on the elliptical, right? Once you get into 4-digit calorie burn, then you start doing your muscles are starting to run out of glucose. Your liver will say, maybe we'll let some of this go. Your pancreas is saying, sir or madam, maybe we should do some, glucagon release here and break some of this apart. And then you'll start releasing more, glucose from your liver from the breakdown of glycogen. But, walking up a flight of stairs isn't going to quite do it. It's not going to quite do it, right? So, yeah. So has anybody ever gone keto, like full on keto or no carb? You lose about 5 or 6 pounds in that first week. It's like, wow, I'm going to lose 5 pounds a week. No, you're not. You're going to lose about 1.5 pounds a week, but that first week you will lose 5, and most of it's water. And most of it's water out of your muscles. As you burn through the glycogen that's stored in your muscles, this is very water soluble and it holds onto a lot of water. It's like having jello in your muscles. So if you're going full on keto or full on like no carbs at all, it'll take you a couple of days. You'll burn through all the glycogen that's stored in your muscles. As you start losing that and converting over to ketotic metabolism, which is more lipid based, you'll start burning more lipids. You won't have nearly as much water holding onto the glycogen in your muscles. And 3 things will happen. 1, you'll lose about 5 pounds. You'll pee a lot. And just most of the arthritis that you have in your joints that you have because you thought you were getting old will go away because you reduce a lot of systemic swelling all throughout your muscles as you dump water out of them. So you'll bring a lot more leanness into your muscular structure from doing that. You dump the glycogen out of your muscles, and so you dump the water out of your muscles. And so you lose most of that 5 pounds is water you sent down the drain.
Well, once you start, eating, participating in carbs again, water can
it'll right back up.
produce again.
You'll gain 5 pounds in a day. You'll gain 5 pounds.
So the water weight will automatically just be produced quicker.
Yeah. Because we'll talk about this when we talk about cells a little bit. Your body will always hold on to or release the water to get you into physiological stasis, right? So it's called osmosis, right? Glycogen has a very high osmotic potential. And so it exists as a gel almost in your muscles. So if you get rid of this out of the muscles, you'll dump the water that was holding it in suspension, and most of the weight will go that way. Not that that's a bad thing. It's 5 pounds that I care about. Go ahead.
Why do you think it burns out muscle than fat?
Why does what?
I heard you mention that it burns out muscles.
You carry a lot of glycogen in the muscle tissue.
Yeah.
right? And that is the sugars that you will use first when you metabolize a lot of sugar. So it's like the order of carbohydrate combustion. It will always be blood sugar first. And then once your blood sugar starts to get low, you will get the sugar back out of your muscles that's stored here because it's most proximate. Once you burn through that, then you will start using the sugar out of the liver. Once you tap that out, once you get rid of that, then you will start moving over to a fat-based metabolism. So if you're going to do like a no carb, low carb, or keto diet, it's going to take a couple of days to really get into actual ketosis, to flush the carbohydrates out. It'll take a couple of days. And for those couple of days, you can feel sluggish, kind of cloudy. Some people even get like a very low grade fever sometimes, kind of hot flashes, because your body is like, sir, I am out of gas and I demand carbohydrates at this second. And you're saying, just learn how to burn fats, man. Just learn how to burn fats. So the pain you feel when you're learning things is the pain your body feels when there's no carbohydrates available to it, right? It'll figure it out, but it takes a couple of days to get rid of the blood sugar, the muscle sugar, and then the liver sugar, just to get to where it'll start burning the fats. It takes longer. It takes longer, and it takes more energy to turn fats into metabolically combustible at a rapid enough rate in order for it to go, kind of molecules. Question?
Well, I was trying to do keto, but so in less than a week, I had lost 8 pounds.
Yeah, water.
Then I got extremely dizzy
Yeah,
for days.
Yeah,
Where I
yeah.
thought I was gonna faint.
yeah,
So my
yeah.
nutritionist is like, you need to add carbs back in.
Mm,
So I did, so I only lost 1 pound.
yeah. That sounds right.
Because everything went right back in. But
Yeah,
how come it's all supposed to be water loss? I mean, the first 10 pounds, you think it's pounds, but it's not. It's water.
it's pounds, but it's water pounds. And it's water pounds that
So
count.
how did I not gain? I drank a lot of water
Where did the water go?
in the toilet.
Yeah, you peed it right. Yeah, you just peed it right back out. Right, you peed it right back out. Right.
So I guess I'm supposed to.
This is the last place you will take calories out of. The last place.
Oh,
Right. So you got to flush out every other source, and that can take a week. That can take a week. But it's like it's like, oh my God, I lost 3 pounds yesterday. Oh my God, I lost 2 pounds today. Oh my God, tomorrow I lost 2 pounds tomorrow. It's not that you're doing something wrong. You're not burning fat yet. You're flushing out the carbohydrates from all the carbohydrate sources, blood, muscle, liver, and what you're losing is water weight. When you plateau out and you start losing a pound or 2 a week, that's when you're burning this. Yeah. So you have to it's like, yay, losing weight fast, losing water fast, but it's still weight. It's still weight. Right?
Yeah.
And it still has belt-sized consequences.
at this point, we'll take everything. It doesn't matter. Water, and so athletes that do like water fast, they're doing it for no reason, basically.
I don't even know what that is.
A water fast,
Oh, yeah.
like
Were you trying to make
yeah.
weight for boxing or?
you don't eat nothing. You do just strictly drink water, no eating. Like they do that to like lose the weight, just like apparently like gain like the muscle. So the water fast.
You'll lose a little. Well, the thing about keto and these paleo diets is, well, let me say a couple of things. One, it's very, very hard to eat absolutely no carbohydrates. There are very few things that you can eat that have 0 carbs. Right? There are trace carbohydrates in like steamed chicken breast. A little, not much, but whatever carbs the chicken was carrying, right, in its muscles is sort of there. It's low. Avocados, awesome, right? Fruit is a non-starter. Don't even bother with fruit, right? There's so much sugar in fruit. So it's like, don't touch that. But what you might know Tim Ferriss, I don't know who Tim Ferriss is, podcaster extraordinaire, right? He has this diet that he came up with that he calls, it's not no carb or keto, it's slow carb. It's mostly protein and fats, but it's mostly proteins. It's not quite keto, but he calls Saturday Fatterday, because like Saturday is the cheat day, and he's like, he eats 4 bear claws, 3 pineapples. It's like shoves as many carbohydrates as he can almost get. He just goes on a full out carbohydrate bender on Saturdays. And what he says that does, you'll gain a couple of pounds back of water on Sunday and Monday by doing that, but your body doesn't completely shut down. Totally, it's carbohydrate burning physiology and totally move over to fat burning. Because it's like, the downside about paleo and like total keto diet is that it wrecks your kidneys pretty hard. You can't live like that. You can do it short term if you're trying to drop a lot of pounds, but you can't live that way without doing like kidney damage. You get like fatty liver disease and coronary artery, all this other kind of stuff. It's almost too much stress that you put in your body. So it's like, it's not a bad idea to get some carbs every once in a while. It's not going to kill you. But if you're really going to seriously do like keto, paleo, slow carb or something like that to lose weight, you need to actually do it and quit screwing around. It's like, you got to follow the rules or it's not going to work. It's like, I'm going to eat nothing but fats and proteins all day long. And then it's like, ooh, Twizzlers, but it's only a snack. It's going to be fine. It's like you screw up the whole damn day. If you're going to do it, you have to not cheat. You have to not cheat. The typical rules for paleo keto, I think it's like less than 50 grams of carbs a day. I think it's around there. So it's like some are going to make it in. And that's just the way that it is. But it's like, if you minimize it, your body will stay mostly in that ketogenic state of burning fats here. But it takes a couple of days to get there. And they're not comfortable days. You get these urges like, I will kill somebody for some M&Ms right now. And I'm going to get a pound of sugar and just eat it with a spoon out of the bag in the Safeway aisle and things like that. Because your body is accustomed to things and it likes what it likes. It likes what it likes. Carbohydrates. What do you think? Questions? I will also say you're all beautiful exactly as you are.
Rivera says differently.
Yeah, everybody's different. Everybody's different. Everybody's different. With me on that?
Self-love.
Who's beautiful? Raise your hand. Who's beautiful? Everybody. You're beautiful. You're beautiful. Perfect. Well, looks like we're just going to get to carbohydrates today. I'm going to do one more thing about carbohydrates. You still got it in you?
Yes.
Perfect. I don't mind taking those little intellectual breaks about talking about interesting things, because it's like, let's rest the brain a little bit. Let's let things settle. Let's talk about like how we actually live on Earth, because we don't do this in our life. What do? We buy those, So it's like, you don't do carbohydrate metabolism with hydrolysis and glycogen production during your day. You eat things and you drink coffee and you move around and you try to get some goddamn exercise every once in a while. And you've heard that you should eat some plants every once in a while, this kind of stuff. I mean, you don't live like this. You live with, in the grocery store, in your kitchen, with your habits of when you eat and what that's how you live. So it's good always, I think, to make sure that we're keeping in mind, not just the details about how things are happening and what's actually happening in our bodies, but also tying them back to the decisions that we actually make in our lives as we live them, With me on that?
Mm-hmm.
Okay.
Yes.
Last 1, 2, 3.
Yes.
You could have said no as well. No, I just want to do more detailed. Who out there has ever had an injury bad enough or good enough to require stitches? You guys live your lives too safe. You had stitches. How long ago?
When I was a baby, it was my eyebrow.
Did they have to get removed, or were they the self-dissolving kind?
I'm not sure, I was a baby.
That makes sense. Ask your younger self. You've heard, nobody you guys need to get out more. My God. Your parents or guardians are keeping you too protected. I blame my own generation here. I blame my generation. Back when I was a kid, my God, it's a miracle we lived as long as we did. My mom picked me up, but I get my mom going home from the hospital on a 1963 Volkswagen Beetle with no safety features whatsoever, with me on her front lap, right, in the front seat of this car. It's like, there were no helmets. You can even buy a helmet for a bike if you wanted to. Anyway, stitches. So you may have heard that should damage be incurred upon you or someone you love, who knows somebody who has had stitches? See, now we're talking, and you learned the cautionary tale, right? That their lesson has taught you. And did those stitches dissolve on their own, or did they have to get them taken out?
Taken out.
Sometimes you still have to get. Where were they? Do you know? Were they deep or shallow?
Around here. So my baby cousin had he held the knife, and his father wanted to take it out, but he was holding on it way too much. So when he,
Sounds like many mistakes were made here
Yeah.
in this whole thing.
so maybe because I'm.
Here, let me yank that
that
knife from your
Had
hand.
it around.
Goodness me.
Oh wait, I did have stitches.
Ooh,
You remember that?
Yes, my wisdom teeth.
there you go. There you go.
And
There
they
you
were
go.
like, you had to remove the
Yeah,
stitches. They
yeah.
were dissolved.
Back in my day. Now sometimes you can get stitches that they dissolve on their own. They dissolve on their own. That is referred to, those stitches are made out of carbohydrates called cellulose. Cellulose. If we remember our glycogen, look kind of like this. Yes? No, it doesn't look like that. It looks like that. Glycogen, right? Just long chains like that. Cellulose is a little different. Let me draw here for a second. Cool. Let me draw another one here. So if you took like two glycogens or something like that, like two long polymers, and what you can start to do you can start to make cross-links between. So it's not just bonds down the chain, you have bonds across the chain. When you do that, you're talking about a different polymer. You're not talking about glycogen. You're talking about, you call it cellulose. This is more down the lines of like what plants do when they make wood or cell walls for plant cells or cellulosic. Insect exoskeletons, arthropod exoskeletons have a lot of cellulose in them. So essentially you take the same chemistry that insects use to make an exoskeleton, but you make a weavable thread out of it. And the cool thing about it is you don't have to grind up a bunch of insects in order to make surgical thread, right? You can take some sugar molecules and the enzymes in a vat, like industrially, and you can make fibers out of it, which is kind of neat. You have enzymes that do a very good job breaking that bond. You cannot break that bond as a human. So when you eat stuff that has a lot of cellulose, you call it insoluble fiber. So when you talk about a high fiber diet, needing enough fiber in your diet, yes, this is what we're talking about. And the fun thing about it is that it goes in one end and out the other end fairly intact. But it does a very good job of, and you know the story is here, keeping things moving in your gastrointestinal system, all kinds of good stuff. One of the best things that you can do for yourself health-wise is eat as much fiber as you possibly can. It's good for about 1 million different reasons in your physiology. We think about things like cows and horses and large herbivorous dinosaurs just eating nothing but plants all day, right? You can't get the energy out of this, so how do they live? This is where the stories of cows having 4 stomachs, keeping bacterial, fungal reservoirs inside of their stomachs. Some fungi and a lot of bacteria can break this bond. So what cows are doing, they're giving as much cellulose as they can to the bacterial colonies that they keep alive in their stomachs and in their intestines that will break that bond, turn it back into glycogen, and they can get the energy back out. You don't do this. So when you eat cellulose, it just goes in one end and out the other. Very good. But again, a polymer of a carbohydrate, that has been bonded together into an arrangement. You do a really good job at breaking glycosidic linkages. You, animal, in your digestion, you do not break the cross link. You don't have an enzyme that does that, right? So it is insoluble fiber, non-digestible, goes in one side out the other. Doesn't mean it ain't good for you, just means you're not getting any calories out of it.
Insoluble fibers is the bond that you can't break, right?
Yeah, what makes it insoluble is that you cannot break the cross linkages. You don't have an enzyme that can break this bond. You only have enzymes that can break that one. Wow, you learned more about carbohydrates today than you ever thought you would. Does it all make sense? So, long story short, the take-home message is hydrolysis, dehydration reactions. How do you attach the molecules together? How do you break them apart? How do you attach carbohydrates together? You use dehydration. How do you attach amino acids? Say it. Dehydration. How do you attach fatty acid shales to glycerol to make a triglyceride?
Dehydration.
How do you attach nucleotides together to make DNA chains?
Dehydration.
How do you break them all apart? Hydrolysis, right? So it's like your body has this toolkit. It's like the IKEA situation. You have an Allen wrench in there. And that one Allen wrench, you use the same reaction for just about everything. It's all dehydration and hydrolysis to make big things out of small and small from big. You guys are awesome. I have good news. Since yesterday was a holiday, right? To keep the lab technicians and the lab managers sane with the timing of things, we typically don't have labs on days when we have a day of the week off. That is true for this week. You guys did an amazing job on lab last week with all of that. Thank you for suffering through. On Thursday of this week, I'll see you at 9:35. And then at 10:55, the rest of the day is yours. Our next lab will be next Thursday, where we'll do some macromolecule stuff in lab and all kinds of good fun. Okay? I'll put an announcement up there as well on Canvas and everything. Thanks so much. I'll see you guys soon. You guys are awesome. Bye. 1, 2, 3. Bye. 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 Wonderful. Thank you.
Thank you. The fourth question here, can I just draw